Hello again. This is Math 2233 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Functions of Several Variables, Graphing Level Curves and Functions of More Than 3 Variables. As always, please be an attentive learner as you watch this video. Another way of visualizing the behavior of a function of two variables is to consider its graph. If f is a function of two variables with domain capital D, then the graph of f is a set of all points x, y, and z in R3, such that z equals f of xy and xy is in D. So just as the graph of a function in one variable is a curve with equation y equal f of x, so the graphs of a function f of two variables is a surface S with equation z equal f of xy. So we can visualize the graph of S as f as lying above or below or maybe through its domain in the xy plane. And here is an example. So for x, y, and 0 we get this, but if we were to plug x and y into the equation of the function, we would have it up here, and this point would be xy, and that is f of xy. Again, this brown is the projection of the surface in the xy plane. So, sketch the graph of y equals f of x. You could call this z equals f of xy is 6 minus 3x minus 2y. You know what to do. Let's see how you did. Okay, what we're going to do is find the intercepts. So if we take y and z to be 0, we get 2, 0, 0. If we take x and z to be 0, we get 0, 3, 0. And if we get if we take x and y to be 0, we get 6. So these 3 points are on the curve. That's a triangle, and the graph is the plane containing that triangle. Now this is a special case of the function z equals f of xy equal ax plus by plus c, and that's called a linear function. And the graph of such a function has the equation this, or this, if we get it equal to 0. So it is a plane in much the same way that a linear function of one variable are important in single variable calculus. You remember how fundamental it was finding the equation of the tangent line. We will see that the linear functions of two variables play a central role in multivariate calculus. Basically, we're finding the equation of the tangent plane. Okay, here's a sketch then in 3 dimensions. So you want to sketch z equal g of xy equal the square root of 9 minus x squared minus y squared. You know what to do. Let's see how you did. Okay, the graph has this equation. If we square both sides, we see that this is of the form x squared plus y squared equals z squared equals 9. So this is the equation of a sphere with center at the origin, region 3. But since z is greater than or equal to 0, because it is the principal square root, the graph is just the top half of this sphere, and you can see that the graph looks like that. It's the top half of that sphere, and it is a hemisphere. And if you're thinking about, or maybe you've heard of engines that are called hemis, hemis have the top of the cylinder where the combustion happens is shaped as a hemisphere. And once upon a time, this was very popular in muscle cars. It's kind of gone out of style, although it still is something that some people will brag about, is that they have a Hemi, and Chrysler was really renowned for this. So anyway, and there are many historical facts. A Hemi Chrysler Barracuda, a Dodge Barracuda once sold for $3.5 million. and in a quarter mile using a 426 cubic inch Hemi. A guy exceeded 200 miles in a quarter mile record. So that's a little bit of a historical thing, and that is a hemisphere. Now note, an entire sphere can't be represented by a single function because it would have multiple values, and as you know, a function has one value. So this is the upper hemisphere, and the lower hemisphere would be that represented by this. And in some graphing formulas and techniques like the TI-83, to get the entire sphere, you'd have to actually graph both of those on the same coordinate plane. Okay, here, this example, we're saying use a computer, and I'll talk about computers later, but we're talking about graphing this Cobb-Douglas production function, and this is one we actually talked about before. This is one that they did the regression analysis to get this. So if we graph that, we get a graph that looks like this, and you can see we're graphing, this is called a wire diagram, but what happens is for k equal 300, that's the value that we get as it goes along. 200, this is what we get, and 100, this is what we get. For L equal 100, this is the branch we get. So we graph a bunch of those, and that tells us what the surface looks like. And you can think about that as just throwing a cloth and sewing it over the wire frame that you have built. Okay, so that shows the values of P for values of L and K that lie between 0 and 300. On both axes. And the computer, this is the way they do it. They draw the surface by plotting vertical traces. You see those there. And these traces, the value of P increases as either L or K increases. And that's what you would expect just looking at the equation. Here's one for you to attempt. Find the domain and range and sketch z equal h of xy equal 4x squared plus y squared. Notice that the coefficients of the x squared and the y squared aren't the same, so you don't expect this to be a sphere. You know what to do. Let's see how you did. Okay, notice that h of xy is defined for all possible values of x and y, so the domain in r squared is the entire xy plane. The range is the set from 0 to infinity. Because if we put 0, we get 0. We're never going to get a negative number, so that's that set of all non-negative real numbers. The graph is an elliptic paraboloid, and we talked about that earlier, and you can see the horizontal traces are ellipses and the vertical traces are parabolas. So this is the graph you get, and that's a little bit of a review, but now we're looking at it as a function of two variables. Now, these things can get much more complicated. Here is a very complicated picture. This is another different one. So you see we can have all of these things, but you notice that we do have maximums and minimums that can happen in here, and we will study those much more later. Now we turn our attention to level curves. So far we have two methods for visualizing functions: arrow diagrams and graphs. A third method, borrowed from map makers, is a contour map on which the points of constant elevation are joined to form contour curves, or also called level curves. So the level curve of a function f of two variables are the curves with equations f of xy equal k, where k is a constant in the range of f. Now, a level curve, f of x equal k, is a set of all points in the domain of f. You see, this ends up being a two-dimensional graph at which f takes on a given value of k. In other words, it shows where the graph of f has a height of k. So, there's a relationship between the level curves and the horizontal traces. And so, the level curves are just the traces of the graph in the horizontal plane, z equal k, projected down to the xy plane. You want to think about what that means. So if you draw the level curves of a function and visualize them being lifted up, the surface to the indicated height, then you can mentally piece together a picture of the graph. So you see, you can have a two-dimensional picture that tells you what the three-dimensional curve really looks like. The surface is steep where the level curves are close together and is somewhat flatter where they are further apart. And here's an example of that. So here's a three-dimensional thing, and at 45, so you see this is the level curve for k equal 45. There's k equal 40, and so if you lift these up, this goes up to 45. The next one goes up to 40, and so on and so forth. And the last one goes up to 20, and that probably is this one right here, although it is not marked. In fact, it definitely is that one, although it is not marked. One common example of level curves occur in topographical maps of mountain regions, and this is one that we see here. The level curves are curves of constant elevation above sea level. So if you walk along one of these contour lines, you neither ascend nor descend. Another common example is a temperature function that was introduced previously, and the level curves there would be called isotherms, places where the temperature is the same. So we're joining locations of the same temperature. And figure 13, which I'm going to show you in a bit, shows a weather map indicating the average July temperatures. And the isotherms are the curves that separate the colored bands. Okay, so you can see here are the isotherms. So along this one, for example, it's 60. And along the other one, it is 70, and so on and so forth. In weather maps of atmospheric pressure at a given time, as a function of longitude and latitude, the curves there are called isobars, meaning barometric pressure, and joining locations with the same pressure. Surface winds tend to flow from areas of high pressure across isobars to areas of low pressure and are strongest when the isobars are tightly packed. That means the winds are more robust, have a higher velocity. A contour map of worldwide precipitations is coming up, and there the level curves are labeled and they separate colored regions, and the amount of precipitation each region is indicated by the color key. And here's a picture of that. And let's see, we did talk about isobars and winds flowing. We already talked about that, and here's the precipitation curve. Okay, but let's return from the applications to talk about a contour map. So we're talking about a contour map with function f, and here's the function f. And so use this contour map to estimate what is f(1), 3, and f of 4, 5. You know what to do. Let's see how you did. Okay, so the point 1, 3 lies partway between the level curve with the z-values of 70 and 80, and if you look at how far it is between the two, you can guess that that is approximately 73. Similarly, we look at 4 and 5, and we can approximate that as being 56. Okay, these visualize surfaces within a single plane, and that's a very clever idea. And so for the forecast, rely on barometric pressure over large areas to predict weather conditions. These are called barometric pressures, isobars, and you can see that this is what happens. A lot of times you see weather maps that look like this. Oceanographers study in part the depth of the ocean, so the depth can be modeled as a function of two variables. Level curves show how the depth changes in different areas. These curves also show possible peaks and valleys in the sea floor. And we've really already talked about the change in temperature around the world can be interested to climatologists, and a function of two variables can define temperatures. Level curves show the regions where the temperature change has been particularly great. So sketch the level curves of this function, z equal f of xy 6 minus 3x minus 2y for these specific values of k. You know what to do. Let's see how you did. Okay, so when you do that, what you'll find that these are planes, but the contour map here is this is going to be a a family of lines, and these are the lines that you get for that. So that is the contour map, and the lines are equally spaced parallel lines because it is a plane. Here, sketch the level curves of this, z equal this for these values of k. You know what to do. Let's see how you did. Okay, what you're doing is you're graphing spheres, and again, this is a family of concentric circles beginning at 0, 0, and they have radius this. Now you can go k equals 0, 1, 2, and 3. It's not defined for more than that, but this is what you get. And you try to visualize these level curves lifted up to form a surface. And in fact, we saw a picture of this before, so that's good, and we really don't have to probably talk more about that. Here's another one where you just sketch some level curves of this function, z equal 4x squared plus y squared plus 1. Let's see how you did. Okay, again, this is the picture that we get, and these are going to be well, you have parabolic traces when z is equal to 0, but the level curves, which is what you're supposed to do, are the ellipses, and you see if you lift the ellipses up, you get the function itself. And this is the equation ellipse that you get when you just set it equal to k. That helps you graph it. Level curves are formed by the intersection of surfaces and planes, and they can be used to find a particular level curve of interest for a function. And so city planners want to know what's below sea level due to flooding, and so that can help you know where that happens. Weather forecasters often determine temperature maps to predict if we're going to have rain or snow. The colder temperatures will give you snow. And mountain climbers must be conscious of the density of air at high elevations. So maps of level curve can show areas where the air density is dangerously low. And the intersection of a surface whose function is air density will tell you where are regions of thin air. And so, for example, we could talk about plot level curves for the Cobb production function, and this is the one that we have. So what we want to do is we want to set this equal to various values of P. And so what we're going to do is we're going to do that. You know what to do. Let's see how you did. Okay, so here we do it for P equal 100. This is for P equal 140, P equal 180, and so on and so forth. So you see these level curves are labeled with the value of the production function. And this helps you realize that for fixed value of P, as L increases, K decreases, and vice versa. Now, a lot of times we end up talking about computer-generated curves, and you can also generate level curves here. And so here's what happens is that this is the level curve for this function, and you see I rotate it, and when I rotate it, I get a different viewpoint. So I see something that's hidden here. And here is the level curve again for this one. And notice that in part C, they crowd together near the origin, and that corresponds to the fact that the graph is very steep near the origin. Now these are very complicated, and we'll talk about a graphical tool that I recommend that's free that you can use. But now we turn our attention to functions of 3 or more variables. A function of 3 variables, f, is a rule that assigns each or to triple x, y, and z in a domain that is included in R3, a unique real number divided by f of x, y, and z. Now, geometrically, this is difficult to understand unless you say, oh, things are functions of t. But I can think of business problems where there are many, many more variables. And here we're talking about t perhaps being a function of longitude, latitude, and time because it changes. So here's a problem for you. Find the domain of f if f of x, y, z is the natural logarithm of x minus y plus xy times sine of z. And you know what to do. Let's see how you did. Okay, well, when you look at this, you realize that the biggest constraint is going to be on the natural logarithm. You can't have this; has to be bigger than 0. So the solution is going to be z is all set points where z is bigger than y. This is a half space consisting of all points that lie above the plane y equals z. Now it's difficult to imagine it, but that means we can gain insight into it by examining its level surfaces. So even if it's in 4 dimensions, we can have 3-dimensional level surfaces. And so if the point x, y, and z moves along a level surface, the value of f of x, y, z remains fixed. And so we can understand its behavior by looking at the level curve. And so here's an example. Find the level surfaces of this function. You know what to do. Let's see how you did. And of course, if I set that equal to k, I get a sphere. So this thing is constant on the spheres. And we can even go into higher variables. So functions of n variables is a rule that assigns z to f of x1 through xn. And a lot of times, if this is a function, we can think about this as being a vector function. So f of x, where x is an n-dimensional vector, is z is some vector c dotted with the vector f, and that can give us at least an equation of a linear function. So you see vectors do come into play here. Okay. I am going to just show you here that the CalcPlot 3D is, and you just can Google this, and this will take you to the site. It's free, and so you see you can graph very complex surfaces. And if you hit this button here, it will give you the contour map. And there are many functions here. I encourage you to go to the site and play around with it. And in fact, up here you can really see the site, the total site itself. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.